to this computer. Okay. So the principle of superposition. Honestly, it's just like a bit of an extension of I don't know how to describe it. You know, kind of like how in physics, the superposition principle is one where you add up the different vectors that impact an object with the intention of finding the net force on that object. That's basically what superposition is in this in the context of linear circuits. So plus minus. Also, sorry for the background noise, but I'm still on campus today. All right. 110 volts, 4 amps, 5 ohms, 2 ohms, 10 ohms, 12 ohms. Okay. And then we're trying to find the voltage here. So, let's see. Okay. Wait, why am I getting pings? Who's pinging me? Okay. So basically there's going to be two versions of this question that we do. So we're going to have the voltage method. Well, not the voltage, well, I don't want to say method, but basically the superposition principle is where you turn off all the other sources, all the other independent sources, but one of them. So for this side, we're going to do the voltage source, and then this side, we're going to do the current source. If I can spell current correctly, current. So on the left-hand side, we're going to have our voltage source here. Oh, I'm going to run out of room here very quick if I'm dealing with something this small. Okay. So there's that. There's that. There's that. Oh, what am I doing? Okay. So think of it like this current source, I'm making this 0 amps. So what happens to a wire if 0 amps travel through it? It's basically an open circuit, right? So we're just going to erase this top part. We're going to ignore it. It doesn't matter to us right now, right? Because this is just like this, basically. So it's an open circuit. No current can flow through it. So we're just going to erase the whole top. We're going to say 5 ohms, 2 ohms, 12 ohms, 10 ohms, plus minus V, 110 volts. So let's not forget the signage. Signage is very important when we're dealing with superposition. It has to be consistent across all versions of it. So here's what we're going to do. The way I'm seeing this is to solve for voltage on this 10 ohm resistor here. I'm going to just start simplifying the circuit like this. So now I'm seeing this is going to be 14 ohms on the side. This is still 10 ohms plus minus V, and then this is 5 ohms. Okay. Here's one fun thing, actually. One of the things you want to keep in mind is that the voltage resistors in parallel have the same voltage across them. Resistors in series have the same current through them. So this is 110 volts right now. That means that if we were to, so we're going to combine these in parallel. The reason we know they're in parallel is if we were to label the nodes B, B, and then C, C. So we know that the equivalent resistance of these two nodes is 1 over 10 plus 1 over 14. Let me get my calculator for this. There it is. 35 divided by 6. So I'm getting my equivalent resistance is equal to 5.83 repeating. So when I redraw my circuit, we're going to get 5.83 repeating, 5 ohms. This is still 110 volts. So we can actually do the voltage division method on this. So keep in mind, so what I was getting at earlier, the voltage across this resistor is also V, which means that the equivalent resistor here is going to have the same voltage there. So the voltage division method is thankfully pretty simple. The way this is going to work. Oh, we have 3 participants now. I wonder who came. Welcome to the call. Keep in mind, the voltage that we're finding is going to be equal to the total voltage, which is going to be 110 times the resistor that you're trying to find. So 5.83 repeating divided by the sum of the resistors that are in the same like string. So 10.83 repeating. Now, if we punch that into the calculator, 110 times fraction 5.83, I'm going to put a bunch of 3's down. 10.83. I get P is equal to, well, not 60, but 59.23 volts is what I'm getting. Okay. So this is our voltage 1. This is not the full answer because keep in mind, we have another independent source in the circuit that is having an effect on that resistor. So we're going to go through and we're going to redo it, only doing it with the current this time. So it's going to be, you're going to have your current source, and then it's going to go resistor, resistor. Now let me ask you this. What happens if the voltage across something is 0? Well, in this case, this, like if I tell you the voltage across this wire is 0, well, you know, if there's no voltage, that really just sounds like it's a wire. So we're going to make that a wire. Now, look at the signs again. This is the important part. If it won't zoom in like that, all weird. Okay. Plus minus, you have your voltage, 10, 5 ohms, 2 ohms, 12 ohms. For this one, let's label our nodes again. A, B in here, C, C. To me, it looks like these 2 resistors are in parallel. So I'm going to combine those. This is 4 amps also. See if I can scroll down a little bit. So my 1 over R equivalent is going to equal 1 over 5 plus 1 over 10. So that's going to be 10 over 3 is equal to R equivalent. That's going to be what, 3.3 repeating? Okay. So let's redraw the circuit. I'm going to redraw it next to it, actually. So check it out. I got this. So this is going to be 3.3 repeating. 2 And then this right here, this kind of goes, like instead of drawing this out like this and then my 12 ohm resistor there, I'm just going to draw it like this instead. That way it looks a little bit neater. So this is my 12 ohm resistor. Now, let's not forget one thing. Let's look at the signs here. Negative, positive. So I'm gonna say positive here. I'm gonna say negative here, and then I'm just gonna keep like the trend going negative, positive. Like see, so I'm gonna go negative, positive, and then positive like that. So in this circuit over here, oh, and then let's do. I don't know. Let's do positive, negative here for the 12. That way it goes positive, negative, positive. See how it kind of all, it's in the same kind of, anyway. So that means, let's look at this, these two sources here. We have positive, negative. So when we come over to this circuit over here, this is going to be labeled positive, negative. I'll do the same on this resistor, and I'll do the same on this resistor because, you know, it just makes sense in the grand scheme of it. As long as you're consistent with your signs. This is consistent with when we did it with the voltage source, and we're keeping it consistent with the current source. So if this is 4 amps, how is it that we can find the voltage here? Because keep in mind, resistors in parallel have the same voltage across them, meaning that this resistor, because it's the combination of two parallel resistors, it has the same voltage. Well, how do we find the voltage there? Well, the way I'm thinking of it is we find the current flowing through that wire. So I'm going to simplify this circuit one more time just to be able to find the current, and then we'll get back to finding the voltage. So this is going to be 5.3 repeating ohms there. And let's not forget our signs, negative, positive, but there's no voltage here because we have lost at this point the voltage indicator in this string here, because keep in mind, the voltage in resistors that are in series, that is different. The current stays the same. So here we have a 12 ohm resistor. Now we can do the current division rule here. So here we have I, and then here we have like I1, and then here we have like I2, right? So if we were to KCL, like if this was node A, and we were to KCL node A, we would get I is equal to I1 plus I2. And we want to find I1. So we're going to do the current division method for this. So current division. Current division also is pretty easy. So we're going to say we want to find I1. So what we do is we say the total current times the opposite resistor. So I'll actually just write it here. So total current 4 amps times the resistance of the opposite resistor divided by the sum of both of those resistors. That's going to be 17.3 repeating ohms like that. And that's going to be our current flowing through I1. We'll put it in the calculator. Any questions while I type it in? Anyone? That's fair, no questions. Okay, so for the current, I'm getting 2.76 amps. And in a way, it makes sense. If you think of it like this also, 5.3, you could say that's just under half of 12, maybe. Let's see, what's 5.3 divided? It's like, yeah. So it's going to have like a little over half of the current flowing through it because it's half the resistance. So now that we know what I1 is here, let's go back up to the circuit here. Now we can find the voltage across this resistor. So how do we do that? Let's not forget Ohm's law, V equals IR. So voltage is equal to, now here's one thing that you want to pay attention to, and I'm going to draw this in a different color. This one's important. Let's look at our signs here, negative, positive. Our current is flowing in this direction. right? Meaning that in this context, it doesn't agree with the idea of passive sign convention. So what we're going to have is we're going to have the current. So our current is, no, shoot, what was it? 2.76, 2.76. Times the resistance of 3.3 repeating. But because it doesn't agree with, like, it's flipped, it's going against what the signage is, I'm going to put a negative in front of there. Right? So then this, do the math, negative 76 times 3 repeating. I'm going to get negative 9.19 volts. That's our voltage across this resistor. Does that mean that you are, no, actually, I'm not going to try to elaborate on anything that's complicated with this. I have one kind of related question. Do you know if there's a discussion tomorrow? Yeah, I think there is. I'm going at least. I think I don't think there's any situation where we don't have a discussion, actually. Discussion section. Like even with exams, we still have them. So this answer here, this is going to be V2, I'm going to call it. Okay, thanks. Yeah, of course. So this will be V2. Yeah, discussion is also going to be good to go ask questions for this, you know. Although here's what I will say. I'm betting that the quiz next week is going to be on like nodal analysis, probably. You know. All right. So the net voltage is the combination of both of them. So we're going to say 59.23 plus, and then we're going to get the value up here. It's with negative 9.19. So if we combine those, we get 50.04 volts. Let's check to see if our answer is right. So see, this is them splitting up the this circuit. And then there you go. Look at that. So it looks like for them, what they did is that when they found the current I2, instead they put the negative in front of the 4 here, making the total current negative. Whereas for me, I worked under the assumption that it didn't agree with passive sign convention. So they actually started it way earlier and put the negative right in there, which kind of makes sense, because if we're thinking of this as like positive negative means our current is flowing this way, the directionality of the independent current source is opposite to that, which means it's acting in a negative fashion. Either way, you get the same answer. As long as you have your signs and you stay consistent with your signs, you'll be good. You'll be set. Okay. Oh, hold on. Do they have any discussion questions with the superposition? Oh, I don't see any discussion questions. Oh, but we don't have the answers for this anyways, huh? Okay. I say let's do one that looks very different. So we're gonna do, let's do this bottom one. This bottom one has a current dependent current source in it. So we want to find V naught, which I'm just going to assume is the voltage across the 20 kilo ohm resistor. So plus minus Okay, 4 kilo ohms, 20 kilo ohms, plus minus V, 5 milliamps, 25 volts, 2.2 I V. Okay. Oh, and then this is I V right there. I don't think we'll have a question exactly like this for the quiz, just because this is a little out there. This is a little hard, I'll be honest. So we're going to do the voltage version here. So let's just start drawing it out. Plus minus, resistor. This is going to be open circuit here. Okay, I'm just going to, there we go. And then this is going to go resistor, current source, 2.2 IV plus minus V, 20 kilo ohms, 4 kilo ohms. You have your current flowing through there. Okay. So here's what I'm going to do actually. 25 volts. Part of me is looking at this and says, hey, you know, there's no danger ever in just doing a KVL. My KVL is going to go along. Okay, hold on. Here's one thing though. We're going to say plus minus. So these are the signs for our things. So KVL, we're going to go in this direction like that. We're going to go counterclockwise. Or I'm sorry, that's just regular clockwise. All right, so 25 plus 4 kilo ohms times I phi minus 20 kilo ohms times. Now, here's one thing though. We don't know the current flowing through there. So this, we don't know it. So let's label our nodes. Hold on. Let's see. Let's try to problem solve this. I may have C, C, C. Okay. Let's KCL node B. Sorry, I should have seen this before I did the KVL actually. So KCL of B has 2.2 I phi going into it. And then we have minus I phi is coming out. And then I'm going to say minus I. Let's call this I right here. Let's set that equal to 0. Now look at this. To me, this looks like 1.2 I phi is equal to I. I combined these and I moved the I over to the other side. So this current, I'm just going to put it in terms of I phi. This is 1.2 I phi right there. So this becomes 20 kilo ohms times 1.2 I phi. And you know what that's going to give me? This is going to give me the I phi. So, man, negative 16 kilo ohms. Oh, no, wait, we can't just do that. Hold on. 20 times 1.2. So I'm going to assume it's just 4 kilo ohms. I phi minus, this should be 24 kilo ohms. I phi is equal to 0. Here I go checking myself. Yep, 24. And then we're going to put the negative 25 on the right-hand side. We're going to combine this. So it's going to be negative 20 kilo ohms. I phi is equal to negative 25. So an I phi is going to be equal to negative 25 divided by negative 20 times 10 to the 3. Are we in agreement there? Ah, okay. So for I phi, my answer is 0.00125 amps. That's also known as 1.25 milliamps. That's not our full answer though, but it helps us. It helps us. So, because look at this. Let's come in here. Let's replace all of our currents. So we know that it's 1.25 milliamps. I'm just going to write it in general form or whatever it's called. 0.00125. What's 1.2 times this value? Shoot. 1.2 times 0.00125. That is going to equal 0.0015 amps. And then this value up here, the 2.2 I phi, that is going to equal this is going to be 0.00275. So here's actually a cool way we can check this. Let's look at KCl again. We have 0.00275 going in. That should be equal to 0.00, running out of here. 125 plus 0.0015. And if you punch that into your calculator, you find that they actually are equal. So it works out so far, which is good. So what is the V? Let's not forget Ohm's law. V is equal to the current, 0.0015, times the resistance, 20 times 10 to the 3. Let's just plug that in. This is only V1 though. This isn't the full answer. Got a whole gang here now. 0.0015 times 20 times 10 to the 3. This is going to be 30 volts. 30 volts is my answer. Part one. Part one of my answer. So I get 30 volts. Our signs look fine. So it looks like it does. One of the things I'm looking for, I don't know how right this is, but I'm seeing the positive sign here and I'm looking at it. It's kind of like it's all in agreement here, you know? So I don't have an issue yet. So let's look at the side with the current source. Node, right. Node, resistor, current source. This is going to be a line because voltage equaling 0 is just going to be that. It's just going to be 0. Right. Oh dear. Forgetting all my resistors today. Okay. 5 milliamps, 20 kiloohms, 4 kiloohms. We have our current flowing through here, I phi. So let's not forget our signs. This is going to go, how were my signs previously? Negative, positive, positive, negative, negative, positive, positive, negative. This is our V. Okay. 2.2 I phi. Perfect. Let's label our nodes. See what we got. A, 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 B, 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 That's it. So here's what I'm thinking. This circuit, I think I have it drawn above, but I don't want to look at it. So how do we find the volt? Almost dropped my laptop. Okay. So here's what I'm thinking. These two resistors are in parallel. Might not look like it, but they share the same starter and end nodes. So if I were to redraw this, you kind of want to think of it a little bit like this. Check it out. You have node B here, and then this kind of splits off. All right, so this is going to split off. Hold on. So this is going to go, this is a 5 milliamps. See us pointing away from the B. And then we're going to have a resistor. And this is all going to join up here at node A. This is the 4 kilo ohms. And because current flows from B to A, so we have current flowing through here. This is I phi. This is the other side. This is the 20 kilo ohms. Positive, negative. And then we have one more thing, which actually goes like this. As you can see, this arrow is pointing towards the B. So that's what I did here. So with this visualization, these are the same circuits like this, but these are clearly in parallel. So we're going to go off that. My thought process is this. I can't find voltage here until I know the current flowing through it. But I don't know the current flowing through it until I can probably combine these and then get somewhat of a formula with these two things. So let's see. Let's just draw it like this. Let's go. Let's say this side is A. This side is going to be our node B. So we have our current source here pointing to A. We have our resistor. We have a second resistor. Then we have our current source. Current source is pointing down to B. This is our 20 kilo ohm. This is the plus is at the B side. Plus is down here. Minus is at the A. That's our voltage. This is our 4 kilo ohm. This is 5 milliamps. Let's combine them. This one's a bit of a headache. 1 over 4 plus 1 over 20. 10 divided by 3. Lovely. This is 2.2 I5. So now we have our circuit. Okay. Part of me is thinking, how did we denote our current in the last question? It was positive to negative. So this was our current here, I like this. So with this, yeah, we could actually do the same thing. So let's say, yeah, this is our node A up here. This is our node B down here. Let's just KCL node A. So KCL node A is going to be 5 milliamps plus I. And then we're going to set that, we're just going to say equals 2.2 I. This gets a little messy, actually. So this one, I'm actually going to look at how I had set this up earlier because we're starting to run out of time and I don't want to be like rushing and getting things wrong. So this is how I ended up doing it earlier. Oh, I actually KVL'd here. Interesting. So the way I had done it earlier today was I did a KCL at A without simplifying the circuit. That way I get IVI, IFV 2.2. This allows me to put the, well, yeah, we're in the same spot here with the equation right here. This is the same spot. And then all they did was we KVL'd the equation. Yes, we KVL'd the equation here just between the resistors. That way we could then replace I with the kind of substitute value here. So that goes into there. We substitute I, and then we just kind of simplify I to get it over to one side. So that gives us I phi. And then we redrew the whole circuit, I believe. Nope, this is a different question. Did we just stop here then? Okay. Well, the 0.005 at that point, if we come back up here to the current source, 0.005 times the 12 to 20 kilo ohm resistor there should give us our voltage across it. And then when we do that, we want to get both of those values. And then we actually want to combine the voltage values. Let's look to see if our math is right. Okay. So let's look on down here a little bit. We have 30 volts for our thing around the voltage. All right, there we go. We got 30 volts. Now let's look here at the left-hand side. See, so with this, if we were to start following, oh, so see, they also did it without fully simplifying it. But if we were to do I is equal, okay, so that would set that equal to that, and then we would KVL. So we got 1 milliamp there. Let's look at the early, actually, let's look at the earlier question to see how we did it there. We got the 1 milliamp. Oh, wait, the 1 milliamp is for the current through this resistor. That's not the I phi value. The I phi would be, if this was 1 milliamp, that would be, okay, hold on. Now you got me checking my work. Okay, actually, let's not do that yet. So you get the 20 volts here. So on the left-hand side here, I got 30 volts right here. It's really small to read. And then on this side, my answer would have been 20 volts. So my total voltage, my net voltage would equal 30 plus 20, which would equal 50 volts there. That's how the work would play out. Yeah. It's not too bad. That question is iffy, especially when you start playing with decimals. All right. So since we're coming up on time here, does anyone have any questions at least? I'm sorry that this study session wasn't as long as we usually do it, but I do also have like an hour drive home that I got to do. And I want to make sure that I'm refreshed for the quiz tomorrow. Does anyone have any questions before you go to bed or call it a night? Anything? Nothing. Well, I think that's awesome. Then that means we did good. Oh, I actually have to go anyway. So thank you for your help. Hey, no problem, Austin. Good luck on the quiz tomorrow. All right. If you go to sleep, make sure you set an alarm. We already had someone miss our first exam, so don't be the second guy to do it. All right, guys. Thanks for swinging on by.